Hello, this is Charlie Thompson, and this is the pre-lab video for Lab 7 on atmospheric stability. So the whole point of atmospheric stability, the reason we really care about atmospheric stability is because if you want to make it rain, you need to lift air up. And so really I'm just going to start over. Hi, this is Charlie Thompson, and welcome to the pre-lab video for Lab 7 on atmospheric stability. Here's what we're going to talk about in this video. We'll talk about how to make rain, which is the whole point of atmospheric stability. We'll talk about lifting mechanisms, different ways that air gets lifted up. We'll talk about lapse rates. Those are the rate of change of temperature of the atmosphere as it just sits there, as opposed to the adiabatic rates. The adiabatic rates apply to moving parcels of air, so that the physical processes going on are completely different in the cooling with the lapse rates and the adiabatic rates. We'll talk about atmospheric stability, what it means. We'll look at some examples. We'll review the critical tasks, and then we'll go over some more examples of how to actually do these problems. So, if you want to make it rain, you need to lift air up. That's pretty much the reason that meteorologists are concerned with atmospheric stability, because if you want rain, you need to cool air, and pretty much the only way to cool air is to lift it up. So to make it rain, you need to have liquid water in clouds. Clouds are made of liquid water, but most of the time the atmosphere, it's not made of clouds, right? There's just water vapor. Water vapor is a gas. That gas is in the atmosphere, but you don't get rain out of water vapor. You get rain from droplets of water. Those droplets of water have to condense out of water vapor, and in order for water vapor to condense, you need to chill the air, and the only way to chill the air is to lift it up. To get liquid water in clouds, you need water vapor to condense. In order to get water vapor to condense, you need to cool the air below the dew point temperature. Once air cools below dew point temperature, you get condensation. To cool the air below dew point temperature, you need to lift it up. Rising air, as it moves, as it rises, the air pressure around it is lower. Remember, halfway up through the atmosphere is 500 millibars. At the surface, it's 1,000 millibars. So as the air rises, the air pressure around it is lower, so the air parcel expands. As it expands, it cools because it's expanding. Rising air expands and cools. As the air cools below the dew point temperature, water vapor condenses. So to make it rain, again, you need to lift air up. So, for example, the maximum specific humidity at 40 Celsius is 48.7 grams. Let's just pretend, let's go to the Persian Gulf and hang out, and let's pretend it's 40 degrees and the relative humidity is 100%. The air is saturated. So if we cool the air down to 20 Celsius, the maximum specific humidity now is only 14.7 grams. So we've gone over this in the last chapter, in the last lab exercise, but it probably didn't occur to you that as the maximum specific humidity comes down, for example, from 48.7 grams to 14.7, the rest of the water, everything in excess of the current max, is going to condense. So we started with 48 grams of water. As the air cools to 20 degrees, the maximum is now 14.7. So there's 34 grams difference between 14.7 and 48.7. Those 34 grams of water vapor will condense and become water droplets. That's where the rain comes from. Everything in excess of the current max is going to condense and become liquid water. As that liquid water condenses, or as the water vapor condenses and becomes liquid, every gram that condenses releases 540 calories of heat, which heats the parcel, which makes it easier for the parcel to rise. So let's keep going. There's 4 lifting mechanisms. There's convergent, convective, frontal, and orographic. This is a nice tie-in with lecture. So convergent lifting, this is, I just stole this screen grab from earth.nullschool.net. This was just a section of the ITCZ with the northeast trades coming in, the southeast trades coming in from the south, the northeast trades coming in from the north. They meet along the ITCZ, and these colors actually represent the amount of rain that fell over a 3-hour period. So you've got the northeast trades, you've got the southeast trades. Where they meet at the equator, the air can't go down, it can't go sideways, so it just goes up. So all along the ITCZ, there's convergent. In fact, the C is for convergent, right? It's the intertropical convergence zone. It's the zone of convergence between the northeast trades and the southeast trades along the ITCZ. So convective lifting, it's pretty simple. The sun shines on the ground gets warm. Ground gets warm. The air next to the ground gets warm. If the air next to the ground is slightly warmer than the air around it, it'll start to rise. As it rises, the air will expand and cool. You'll get condensation. Sun shines on ground, warms air. Frontal lifting is when a warm air mass, here's a warm air mass, and a cold air mass collide. In this case, the cold air mass is moving along. The cold air runs into the warm air. The warm air gets lifted up because of temperature differences. The warm air is less dense than the cold air, so the warm air always goes up. So in a front, you have two different air masses, a cold air mass and a warm air mass. And when they meet, the warm air mass, the warm air is forced up always. Warm air always goes up. Orographic lifting is the most consistent, the highest rainfall totals. The average, that 89.5 feet recorded 1 year at Mount Wailea. The 89.5 feet recorded in Cherrapunji in India, the monsoonal rains there, was orographic. The warm, moist air coming in off of the Indian Ocean runs into India and the Himalayas, gets lifted up by the mountains. Doesn't matter if it's stable, doesn't matter if it's unstable. If you're air and you run into a mountain, you're going to get lifted up. So as the air gets lifted up, it expands, it cools, you get condensation, you get rain on the windward side. But then on the other side, if there's no more mountain to lift the air, no more lifting, no more expansion, no more cooling, no more condensation, no more rain. So the downwind or leeward side has a rain shadow. So here we can see some trees, although those look like redwoods, which don't exist in the Sierras. Those would be over in the Coast Range. They could be giant sequoias. We have those in the Sierras, but they look like coast redwoods, so it's a bad stock picture. This, however, is on the east side of the Sierras. You get a good comparison between the west side, the windward side, and the leeward rain shadow, Great Basin desert side. So as an example, what happens, air comes in off the ocean, it gets lifted up. As it rises, it expands and cools. It hits lifting condensation level at some point. And then as the air continues to rise and cool, you get more and more and more condensation, and then everything in excess. So we could actually figure this out. That would be a fun. Yeah, here's a good opportunity. You can check your understanding of how this works. So if you have air with a dew point temperature of 20 Celsius, you can look it up and figure out what the maximum specific humidity is. As that air continues to rise and cool, it's cooling to 8 Celsius. So you could look up and see what the maximum specific humidity is at 8 Celsius. So everything over that fell as rain. It condensed and fell as rain. Everything, so the max at 20 minus the max at 8. Let me say that again slowly. So the maximum specific humidity at 20 degrees Celsius minus the maximum specific humidity at 8 degrees Celsius. The difference between them is how much water vapor condensed. And then once you run out of mountain, once you run out of lifting, there's no more cooling. So the cloud development stops, the condensation stops. And often what will happen is the air sinks. Sinking air heats at the dry rate. So let me back up and start over. In a nutshell, air rises and cools at the dry adiabatic rate until it cools to the dew point temperature, and then when you have condensation, the condensation releases heat, which slightly warms the air, so now it cools at the moist rate of 6 Celsius, but sinking air always heats up at the dry rate. So the air is going to rise and cool at the dry rate until it cools to the lifting condensation level, until it cools to dew point temperature. Then you get condensation, and it cools at the moist rate. but once it sinks, it's going to heat up at the dry adiabatic rate of 10 degrees. So convergent lifting along the ITCZ, air comes together and rises. Convection, sun shines on the ground, warms air. We've got frontal, warm air mass, and a cold air mass. The warm air mass always gets lifted up. Always, always, always. And then we've got orographic, air runs into a mountain, gets lifted up. Stability. The term stability refers to the tendency of an air parcel to rise. And if it rises, remember it's going to expand and cool. You can get condensation. If it stays where it's at, you're not going to get any cooling. And if it sinks, you're going to get heating. So when we're talking about stability, we really kind of divide it up into, is it rising or not? Is it unstable or not? An air parcel that is warmer than the air around it is unstable and it'll rise. An air parcel that's colder or the same temperature, it's either going to stay where it's at or it'll sink, and so it's stable. If it stays where it's at, it's not going to cool, we're not going to get rain, so it's stable. Hot air balloons are a great example of this. If you just remember that if the parcel is warmer than the air around it, it's going to rise like a hot air balloon. Nobody goes cold air ballooning because they don't rise. So in determining the stability of a parcel, because later we'll talk about stability of the atmosphere, and you can just like look at the atmosphere, look at the environmental lapse rate, and get an idea what the stability of the atmosphere is. But you can also talk about the stability of an individual parcel. So if the parcel is warmer than the air around it, it's going to rise like a hot air balloon. I'd probably write that down. I'd get that as a tattoo at this point. That's how important that is. Warm air rises because it's less dense. It's not that hot air rises magically. Hot air rises because it's less dense. All right, rates of cooling and warming. I think this is one of the more confusing parts of this chapter that has many confusing parts. There's 4 different rates. They are grouped into 2 different categories. So the first category is the rate of change of the atmosphere as it's just sitting there. Remember, the atmosphere, the troposphere, is warmed by the surface. So as you get away from the surface, the troposphere cools. It's just like sitting closer to a campfire. As you move away from the surface, the temperature drops at one of the lapse rates. So the lapse rates, and there's 2 of them, they apply to the unmoving atmosphere. There's the normal lapse rate, which is an average of 6.4 Celsius degrees. And then there's the environmental lapse rate, which is what it actually is. It's measured all over the world with weather balloons many times a day to figure out what the environmental lapse rate is, and that tells us what the chances of rain are. So the environmental lapse rate, it's what it really is. It will always be given to you in the problems. I will always have to tell you what the environmental lapse rate is. It's nothing you'll have to calculate. It will always be given. I know that's always a concern of students is, well, do I have to calculate this or is it given? The environmental lapse rate will always be given to you. So if we've got the unmoving atmosphere, those are lapse rates, the environmental and the normal lapse rate. The environmental lapse rate is whatever it is. If we're talking about a moving parcel of air, they are cooling and in some cases warming for a totally different reason. The lapse rates exist because the troposphere is heated by the surface. As you move away from the troposphere, the atmosphere just gets colder. However, if you have a moving parcel of air, those are going to heat or cool at the adiabatic rates. A rising parcel of air will always cool by 10 degrees. A sinking parcel of air will always heat at the rate of 10 degrees of warming for every kilometer it goes down. Once a parcel cools to dew point and condensation begins, that condensation releases heat, which slightly warms the parcel. So there's cooling because of expansion and heating because of condensation. So the moist rate is the rate you use after the parcel cools to 100% relative humidity, after the parcel cools to dew point temperature. Once condensation starts, it cools more slowly. So the dry adiabatic rate of 10 degrees and the moist adiabatic rate of 6 degrees apply to a moving parcel of air. Moving parcels of air, the adiabatic rates, The word adiabatic refers to a change in temperature of a moving parcel without a loss or gain of heat. So as the parcel rises and expands, it cools. That's why it's cooling. It's cooling because it expands. As a parcel sinks, the air pressure around it increases, so it gets smaller. As it gets smaller, it's compressed. As it's compressed, it gets heated up. This is the same principle of a diesel engine. Diesel engines heat by compression. The pistons inside the engine compress a fuel-air mixture until it gets so hot just because it's compressed that it explodes. If you've ever used an air pump, a bicycle air pump to pump up a bicycle tire, you'll know that the pump gets hot. That's partially because of the compression of the air. If you let air out of a tire, the air coming out is cool. It's cool because it's expanding. It's not just cool, you don't feel cool just because the air is blowing on you. If you actually had a thermometer, the air coming out of a tire would be cooler than the air in the room. The air coming out of a tire as it expands would actually be cooler than the air inside the tire, because as the air expands, it cools. So, adiabatic refers to a change in temperature without a gain or loss of heat. And that heat, the heating, once it's cooling at the moist rate, that's the latent heat of condensation. Rising air cools through expansion. Sinking air warms through compression. Rising parcel expands and cools 32 degrees, 1 kilometer, 22 degrees, 1 kilometer, 12 degrees, 1 kilometer, 2 degrees. Sinking parcel of air is going to heat 10 degrees per kilometer. So 1 kilometer, 12, another kilometer, 22, another kilometer, 32. Rising parcels of air expand and cool. Sinking parcels of air compress and warm. Rising air expands and cools by 10 Celsius degrees per kilometer. Dry adiabatic rate. That's the dry adiabatic rate. That's the rate that air cools by expansion or heats through compression, 10 degrees Celsius per 1,000 meters. Once the parcel cools to dew point, water vapor condenses and releases the latent heat of condensation. So it's cooling 10 degrees by expansion. That's why I said a rising parcel of air will always cool 10 degrees per kilometer. However, once you get condensation, it's going to release about 4 calories of heat. So the moist adiabatic rate is 6 degrees of cooling. There's 10 degrees of cooling, 4 degrees of heating for a net cooling of 6 degrees of cooling. The moist adiabatic rate, 6 degrees per 1,000 meters. The moist rate represents 10 degrees of cooling and 4 degrees of heating for a net of 6 degrees of cooling. The lifting condensation level is the altitude at which a parcel cools to dew point temperature and condensation begins to occur. So the lifting condensation level and the dew point temperature, those are related. We'll talk more about them in a minute. So as an example, if we have a parcel of air on the ground at 20 degrees and it's got a dew point temperature of 10 degrees, as it rises 1 kilometer, it's going to cool by 10 degrees. Once it cools to dew point, that is the lifting condensation level. Once it cools to 100% relative humidity, once it cools to dew point temperature, you get condensation and it'll start cooling at the moist rate. And as long as you keep lifting that air, it'll keep cooling at the moist rate. So you can see dry air, or air before it starts to condense, cools at 10 degrees. Once you get condensation, the air starts to cool at 6 degrees per kilometer. So if we're talking about parcels, if you have a parcel that is cooling more slowly than the air around it, if you have a rising air parcel that's cooling more slowly than the air around it, that parcel will be warmer than the air around it, and so it'll rise and it's unstable. If the parcel cools faster than the air around it, the parcel will get colder than the air. It'll be stable because the air in the parcel will be colder than the atmosphere around it, and it won't rise. It's a cold air balloon. So here we have a couple examples. We have, and again, I will always have to give you the environmental lapse rate. So the environmental lapse rate is given as 12 degrees. So 12 degrees, and right off the bat, I can tell you this example is unstable. Well, if you're if you're reading the caption, you know it's unstable. But 12 degrees of cooling of the environment is a faster rate of cooling than 10 degrees. So if the environmental elapsed rate is higher than the dry adiabatic rate, we say the atmosphere is unstable. So if the parcel starts to rise and cool, even if it cools at the dry rate of 10 degrees per kilometer, it doesn't matter. The parcel is cooling 10 degrees per kilometer. The air around it is cooling 12 degrees per kilometer. The air every kilometer is going to be another 2 degrees colder. So you lift it up, it cools by 10 degrees. The parcel cools by 10 degrees through expansion down to 15. The atmosphere cools 12 down to 13, so the parcel is 2 degrees warmer. So it'll keep rising. At 2 kilometers, it cooled another 10 degrees down to 5. The atmosphere cooled off by 12. So now the atmosphere is cooled down to 1 degree. The parcel has cooled down to 5 degrees. The parcel is 4 degrees warmer than the atmosphere. So at 3 degrees, the parcel is now cooling another 10 degrees down to -5. The parcel cools another 12. The parcel's -5. The atmosphere around it's -11, so the parcel is now 6 degrees warmer. It's just going to keep rising faster and faster. So conditions, if you have a high environmental elapsed rate, an environmental elapsed rate greater than 10, if the environmental elapsed rate is greater than 10, then a rising parcel of air will become unstable no matter what. Okay, so let's look at another example. So the ELR in this case is 5. So if the ELR is 5, it doesn't matter what rate the parcel cools at, the parcel will cool faster, right? Because the two rates that the parcel can cool at is either 10 or 6. So even, and in this example, they've got the parcel cooling at 10, the air around it cooling at 5. So at 1 kilometer, the parcel is cooled to 15, the air around it is cooled to 20. The parcel is 5 degrees colder. It's a cold air balloon. It's just going to sit there. It's not going to rise. It'll probably sink, actually. But even if that parcel was cooling at the moist rate, it would have cooled down by 6 degrees, down to 19. The air around it is 20, so the parcel would still be colder. The parcel would be stable. So if the ELR is less than 6, the atmosphere is stable no matter what. If the ELR is greater than 10, the atmosphere is unstable. The higher the number of the ELR, the more unstable the atmosphere is. So here we've got an example of a parcel at the surface at 40 degrees with a dew point of 20 degrees. And the environmental elapsed rate, it looks like it's 8 degrees. So when you're given these problems, I'm not going to necessarily give you diagrams, but I would give you, you've got a parcel of air, it's 40 degrees, the dew point temperature is 20 degrees, or I could say you've got a parcel with you've got a parcel at the surface at 40 degrees, and the specific humidity is, I would just look it up on the table, find what the maximum specific humidity is at 20 degrees. I think it's 14.7. So whatever it is, if I give you that maximum, if I give you the specific humidity of a parcel, you can find the dew point temperature. If I give you the dew point, you can figure out what the specific humidity is of the parcel. So in this case, the atmosphere is cooling at 8. And I would just go, well, we're lifting it up to 6 kilometers, looks like. So I would say, well, it's cooling 8 degrees. It's going up 6 kilometers. 6 times 8 is 48. So the temperature at 6 kilometers is going to be 40. Temperature at the surface minus 48. So the atmosphere is going to be -8. And indeed looks like I'm exactly right. So the atmosphere is -8. Our parcel starts to cool at the dry rate. So if our parcel cools, as it rises and cools 2 kilometers, it's going to cool down to 20 degrees. The atmosphere around it has only cooled by 16 degrees, so the atmosphere is going to be 4 degrees warmer. So even though we've hit dew point temperature, we've hit the lifting condensation level, and now the parcel is going to start cooling at the moist rate. At 2 kilometers, you can see the parcel's stable. Here's the temperature scale. On the left-hand side, it's colder. On the right-hand side, it's warmer. I like these kind of diagonal graphs because you can look and see, well, who's colder? The parcel is to the left, so the parcel is on the colder side. The red line represents the atmosphere. So the parcel's colder than the atmosphere, so the parcel is stable. As the parcel starts to rise, or continues to rise, though, now it's going to cool by 6 degrees. The air around it's cooling by 8 degrees. So at 4 kilometers, or after lifting for 2 kilometers, they're now the same temperature. Our parcel has risen and cooled by 32 degrees. Our parcel has risen and cooled by 32 degrees. So if the parcel keeps rising, as soon as it goes above 4 kilometers, the parcel is cooling by 6 degrees, the atmosphere is cooling by 8 degrees, so the atmosphere will be colder, the parcel will be warmer. As soon as it's above 4 kilometers, because the parcel is warmer, it'll be unstable. So if I asked you this on a test or exam question or one of the lab questions, I would give you, given a parcel of air with a surface temperature of 40 Celsius, dew point temperature of 20 degrees, given an environmental lapse rate of 8 degrees, what's the temperature of the parcel and the atmosphere, and is the parcel stable at 2 kilometers? And you'd say, well, at 2 kilometers, it's now at dew point temperature. At 2 kilometers, the parcel is colder than the air, so the parcel is stable. And then if I asked you the same thing at 6 kilometers, you should be able to tell me the temperature of the atmosphere, the temperature of the parcel. If you know the temperature of the parcel, you just look it up. Let's say the parcel is, let's see, what was it? It was 20 degrees, and then it rose 4, so it cooled. Parcel's -4 because it rose 4 kilometers and cooled 6 degrees per kilometer. So it cooled 24 degrees. It was 20. 20 minus 24 is -4. So the parcel's -4. So if you know what the temperature is, all you got to do is look it up on the max specific humidity chart and say, well, if the temperature is 4 Celsius, the maximum specific humidity is this, and that's what it'll have. Everything in excess of the maximum. And then I could ask you. So we know what the dew point temperature was, 20. We can look up the maximum specific humidity. The parcel is now -4 degrees. We can look up the maximum specific humidity, and I could ask you how many grams of water vapor condensed from 2 kilometers to 6 kilometers, and that would just be the difference between the max specific humidity at 20 Celsius, because that was dew point, and then the max specific humidity at -4 Celsius. So another example, in this case, we've got an ELR of 12, so we know that it's got to be unstable, right? If the parcel cools at the dry rate, it'll still be cooling more slowly. The atmosphere is cooling at 12, our parcel's cooling at 10. And then it's going to hit lifting condensation level, it's going to hit dew point temperature, now it's going to cool at the moist rate. So over here we have the temperature of the atmosphere, and this is exactly how I would bust out a sheet of scratch paper. I like to have the atmosphere on the right-hand side, but whatever. So I would just go, here's the atmosphere, 1 kilometer, 2 kilometer, 3 kilometer, 4, however many kilometers of lifting that question has, I would just write down that many, and then 12. So just subtract 12 every time. 12, 12, 12, 12. So at 4 kilometers, the temperature of the atmosphere is -8. It should have cooled, it was at 40. It should have cooled 48, right? 12 degrees per kilometer, 4 kilometers, 48 degrees of cooling, 40 minus 48, -8. Our parcel at 2 kilometers, it rose and cooled by 10 degrees. So now it's 2 degrees warmer than the air around it. So it's going to keep rising. Now it's 20. Now it's 4 degrees warmer. It's going to keep rising. But now it starts cooling at the moist rate. So it's going to cool even more slowly. 14 and 4, 8, -8. The farther it goes up, the bigger the difference between the temperature of the parcel and the air around it, the faster it's going to rise. This is how you end up with hurricanes and tornadoes and thunderstorms, is when the ELR is extremely high. And then here we've got that diagonal graph again. So the purple indicating the temperature of the environment. And you can see the dry adiabatic rate and the moist adiabatic rate with the lifting condensation level. I'm not going to make you do these graphs, but I think, like I said, they're useful because you can see every kilometer the atmosphere is on the colder side of the parcel. Well, what if the ELR is 9? So that's in between, right? So goes up a kilometer, cools by 9, 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 down to -5. Okay, so our parcel initially is going to cool faster. Everything's 40 degrees at the surface. The parcel's 30, so it's a degree colder. Now it's 20. Now it's 2 degrees colder. But it's going to hit the lifting condensation level at 2 kilometers. So now it's going to cool by 6 degrees to 14. Now it's warmer. The parcel is 14 degrees. The air around is 13. It's going to keep rising. And now at 8 degrees, at 4 kilometers, the parcel's 8. The air's 4. It's going to rise faster. Now the parcel's 2 degrees. The air around it's 5. It's going to rise even faster. And then if we look at this is the same kind of graph we were just looking at, where initially, because the parcel cools faster, it gets colder, but then as it cools slower, it switches places, and above, looks like 2.5 kilometers or so, the parcel is going to be warmer than the air. It's going to keep rising. Well, what if the ELR is less than 6? If the ELR is less than 6, it doesn't matter what rate the parcel cools at, it will never become unstable. The parcel's cooling at 10, the air is cooling by 6, so already the parcel's 10 degrees colder than the air around it. As it keeps rising, it's going to keep getting colder because it's cooling by 6 degrees now, and the air is only cooling by 5. So no matter what, let's look at that graph. No matter what, the parcel is on the cold side because the ELR was 5. 5, as you know, is less than 6. So if the ELR is less than 6, the atmosphere is going to be stable. The atmosphere is going to be stable. Again, now we're talking about just general. If I give you the ELR, if the ELR is less than 6, the atmosphere is stable. If the ELR is greater than 10, the atmosphere is unstable. And if the atmosphere is in between, we call that conditional instability or conditional instability, conditionally unstable. We don't know what's going on with the parcel because it's going to depend on the parcel. That if the ELR is in between 6 and 10, it's just going to depend on the specifics of that particular parcel, how much water vapor it has, how fast it's going to cool. So hopefully that wasn't confusing, but if it is, you can always back it up and watch it again. Again, if the ELR is greater than 10, completely unstable. The atmosphere is unstable. Doesn't matter what rate the parcel is going to cool at, the atmosphere will cool faster than the parcel. ELR less than 6, no matter what, the parcel is going to cool faster, the parcel will get colder, the parcel will be stable. So I thought I would write down what your critical tasks are. Like, I know, and in fact, for some of you, the best thing to do might be to back up and watch that whole thing again. I know that there's an enormous amount of information being thrown at you very quickly. And one of the bewildering things is, oh my God, what am I supposed to do? Well, here's the things that I think you should be able to do at this point in time. If I give you the basic information of an air mass, you should be able to find the specific humidity, the dew point temperature, the relative humidity, and the lifting condensation level. So if I gave you information about an air mass, if I tell you its temperature, and then either if I give you the temperature and either the relative humidity or the dew point temperature or the specific humidity, if you know the specific, you can figure out the relative. If you know the specific, you know the dew point temperature. If you know the dew point temperature, you know the specific because you just look it up on the table, and then you can use it to calculate the relative humidity. If you know the dew point temperature, you can use that to calculate the lifting condensation level. So really, I just have to give you one of these, the temperature of the parcel, and then either the specific humidity, dew point temperature, relative humidity, and you can calculate the other two and the lifting condensation level. If I give you the environmental lapse rate, which I always will, you should be able to cool the atmosphere appropriately. So if the ELR is 9, you just subtract 9 every kilometer you go up. At this point, you should be able to cool the parcel at the correct rate. A rising parcel of air is going to cool at the dry rate until it cools to the dew point temperature. The altitude that it cools to dew point temperature is the lifting condensation level. So once it rises to the lifting condensation level, it stops cooling at the dry rate, starts cooling at the moist rate. So you need to know the dry rate's 10, the moist rate is 6. You can calculate the lifting condensation level, the dew point temperature, so you know at what point it's going to switch. It's going to switch and cool at the moist rate once you cool it below the dew point temperature, which will happen at the lifting condensation level. So you should be able to figure out all of those things. Yeah, you should be able to compare the temperature of the parcel and the atmosphere to tell me if it's stable or not. If the parcel's warmer, it's unstable and it keeps rising. If the parcel's colder, then the parcel's stable and it stops rising. So if I give you a problem and say we're going to lift it up to 4 kilometers, and then after it gets lifted to 4 kilometers, it's going to be on the other side of a mountain and it's going to sink down to 1.5 kilometers, you should be able to heat it by 10 degrees every kilometer the air sinks. So, can you find an air mass's specific humidity, relative humidity, temperature, dew point, and lifting condensation level? Hopefully. Can you calculate temperature changes at the ELR? And the ELR will always be given. When do you use the DAR? When do you use the MAR? So the answer to that is you use the DAR. A parcel is going to cool at the dry rate until it cools to dew point temperature. And then it's going to cool at the moist rate of 6 degrees. Can you calculate temperature changes at the MAR and DAR? Well, I know it's math, but it's just subtraction. So cooling at the moist rate, can you subtract 6? And then cooling and heating at the dry rate, can you subtract by 10 and add by 10? That's pretty much it. So I know that there's math, but it's just subtraction. Maybe multiplication if you want to get fancy with the ELR. Like if with the ELR, if I told you the ELR is 10 degrees and we're going up to 5 kilometers, what's the temperature of the atmosphere? You can just go, well, 5 kilometers lifting, 10 degrees per kilometer. It's going to be cooler by 50 degrees. So you don't actually have to calculate the ELR every kilometer unless I ask you for some intermediate value. Like what's the temperature of the environment at 3 kilometers? You go, well, it's going to be 30 degrees colder, right? Given an ELR of 10 in this example. And can you tell me if the parcel's stable or not? All you have to do is look at the temperature of the parcel and tell me if the parcel's warmer, it'll rise, it's unstable. If the parcel's colder, it's stable and it's not going to rise. That's pretty much it. So those are the big ideas for Lab 7. Like I said, for some of you, if you found that confusing, I would back it up and watch it again. Turn the captions on. That might also be helpful. If you have questions, please, I beg of you, come to Zoom hours, send me a text, call me, send me an email. Yeah, I'm not getting whatever concept you're not getting. I'm pretty sure just about all the difficult things that we will ever talk about, 5 minutes of conversation would help you figure it out and you'd be good to go. So big ideas. The atmosphere cools at the environmental lapse rate, whatever that is. A rising parcel cools at the dry rate until it cools down to the dew point temperature. Then it cools at the moist rate. Parcel cools at the dry rate until it cools to the dew point temperature. To find the dew point temperature, you need to know the specific humidity of the parcel. I will always give you either what the specific humidity is or the dew point temperature or the relative humidity. Like I keep saying, if you know one of those, you can look it up on the maximum specific humidity chart and figure out what the other three are. So if you know what the specific humidity is, you look it up on the maximum specific humidity chart and find the dew point temperature. More review, there's two types of rates. There's the lapse rate, which applies to the environment. And then if it's a moving parcel, you're using one of the adiabatic rates. Yeah, to determine which rate you're using, you just need to ask who's moving. Are you trying to figure out what temperature the atmosphere is? If you're looking for the atmosphere is part of the environment, you're going to be looking at the environmental lapse rate. If you're trying to find the temperature of a moving parcel, that's going to be one of the adiabatic rates, the dry rate until it cools and you get condensation, then it's going to cool at the moist rate. As you go up through the atmosphere cools at the environmental lapse rate. The environmental lapse rate will always be given to you. The atmosphere cools at the environmental lapse rate. If the ELR is 8, that means the atmosphere gets 8 degrees cooler every kilometer you go up. So if I asked you what the temperature of the atmosphere is 5 kilometers above the surface, you just go, well, 5 kilometers times 8 degrees per kilometer. It's going to be cooler by 40 Celsius degrees. So if you have a rising parcel is going to cool by the dry adiabatic rate until it cools to dew point temperature, rises to the lifting condensation level. The lifting condensation level is the altitude at which it cools to the dew point temperature. After it cools to dew point temperature, it's going to cool at the moist adiabatic rate of 6 degrees per kilometer. LCL. So LCL is the lifting condensation level. The lifting condensation level is the elevation at which a given parcel of air or an air mass will cool down to 100% relative humidity. And for this lab, I'm just going to go back and forth and call things parcels of air, which usually means a moving body of air, or an air mass, which is usually a continent or really large blob of air with uniform temperature and humidity. I'm going to use air mass and parcel. I'm going to go back and forth. Don't worry about it. I'm referring to the same thing, which is just the temperature of a blob of air. think a cloud-sized blob. That's probably a parcel, something that could cover half the United States. That's going to be an air mass, but for now, don't worry about it. So to find the lifting condensation level, you need to find the difference between the current temperature and the dew point temperature to find how many degrees of cooling. And then you just divide that by 10 to get how many kilometers of lifting you'll need to cool that parcel of air to the dew point temperature. So again, LCL, it's the elevation that a parcel will cool to dew point temperature at. Rising parcel, it's going to cool by 10 degrees, the dry rate, until it hits the dew point temperature. Water vapor starts condensing and releasing heat, which makes it cool by 6 degrees, which is the moist adiabatic rate. The dry rate is 10 degrees of cooling per kilometer of rising, which is also 1 degree per 100 meters, which is really convenient. So we find current temp minus dew point temp, divide by 10 to find how many kilometers it has to rise to cool to dew point temperature. So if the parcel needed to cool, if you found the difference and the difference was 20 degrees, it's going to need to rise 2 kilometers. If the difference between them is 37 degrees, that would have to get lifted 3.7 kilometers. Let's do an example. You're given an air mass at 25 degrees Celsius with a specific humidity of 5 grams of water vapor per kilogram of air and an environmental lapse rate of 8 Celsius degrees of cooling for every kilometer you get above the ground. I will always have to give you the temperature of the air mass and the specific, something about the humidity. I could give you the temperature and the relative humidity, and then you could calculate the specific humidity. I could give you the temperature and the specific and ask you to calculate the relative. But I'll have to give you the temperature and starting something about the humidity, either the specific or the relative humidity, and I'll always have to tell you what the ELR is. And in this case, I've said we've got an air mass. The assumption is that the temperature of the parcel or air mass is the same as the atmosphere when the parcel's on the ground. So in setting up these questions, I'll say, you've got an air mass, you've got a parcel at this temperature. That's also the temperature of the ground at 0 kilometers above the ground. So the questions I'm going to ask you, what's the relative humidity? What's the dew point temperature? What's the lifting condensation level? What's the temperature of the air mass and the atmosphere at 5 kilometers higher than when you started? And in this case, we're just starting at sea level. So we're given an air mass at 25 degrees Celsius with a specific humidity of 5 grams per kilogram and ELR of 8. What's the relative humidity? Well, the specific humidity is 5 grams per kilogram. That was given. If you look up on the chart, the maximum at 25 Celsius is 20 grams. So we have 5 grams. The maximum is 25 divided by 20 times 100 is 25%. So to find the dew point temperature, in this case, what's the dew point temperature? Well, the specific humidity is 5 grams, which is in between 3 and 4. I think some of the other ones I gave you were always even, like, well, if you have 5.1 grams, well, the dew point's 4. If you have 4.8, the dew point's 3. But condensation won't start until that air cools to the dew point temperature, so you pick the colder temperature. In this case, it's 5, so we have 5 grams, so condensation won't start at 4, but condensation will start at 3. So the dew point temperature in this case is 3 degrees Celsius, because that was the colder, because the grams of water vapor fell in between two of the values. So we're given an air mass, it's the same air mass, 25 Celsius, specific humidity of 5 grams. What's the lifting condensation level? Well, the temperature on the ground is 25 degrees Celsius, and the dew point temperature is 3 degrees Celsius. So the parcel has to cool by 22 Celsius degrees. The dry rate is 10 degrees of cooling per kilometer of lifting, or 10 degrees of heating for every kilometer of sinking. So 10 degrees cooling for every kilometer we go up. To cool 22 degrees, it has to rise. 22 divided by 10 is 2.2 kilometers. So the lifting condensation level is going to be 2.2 kilometers. It's 2.2 kilometers because we started at sea level. Lifting condensation level is 2.2 kilometers higher than our starting altitude. So what's the temperature of the air mass and what's the temperature of the atmosphere at 5 kilometers? Atmosphere is easy. The ELR is 8. We're going up 5 kilometers. 5 times 8 is 40 degrees of cooling. We started at 25. 25 minus 40 is negative 15 Celsius. So the temperature of the atmosphere is negative 15 Celsius. The temperature of the air mass. So we know that the dew point temperature is 3 Celsius. We know the lifting condensation level is 2.2 kilometers. So the parcel is going to cool to 100% relative humidity at 3 degrees. It's going to cool at the dry rate until it cools to 3 degrees. It's going to be 3 degrees at 2.2 kilometers above the surface. So now we've got a parcel at 3 degrees at 2.2 kilometers above the surface, but we want to go to 5. So from 2.2 to 5 is 2.8 kilometers. 2.8 kilometers, and it's now going to cool at the moist rate. The moist rate is 6 degrees of cooling for every kilometer up. So 2.8 kilometers of lifting, 6 degrees of cooling per kilometer is 16.8 cooler. The parcel was 3 Celsius at 2.2 kilometers, and then it's going to cool by another 16.8. So 3 Celsius minus 16.8 Celsius, the temperature of the parcel is negative 13.8 degrees Celsius. Is it stable? Well, the temperature of the parcel is negative 13. The air around it is negative 15. So the parcel is warmer. It's a hot air balloon. It's unstable. It's going to keep rising. The parcel is warmer. Parcel is unstable. Oh, another example. Man, that's exciting. Nothing better than doing math. So what do we have? We have an air mass at 14 Celsius. It's got a specific humidity of 5 grams per kilogram. So right off the bat, we go, oh, dew point temperature is 3, right? From the last problem. ELR is 9. So at first, our parcel is going to cool faster than the atmosphere until it cools to dew point temperature. Then the parcel is going to cool more slowly because the ELR is in between the moist rate and the dry rate. I would, if you didn't catch all that, if I said it and you just heard the words and went, what the hell? Back it up, listen to that again, because that was good. We know that the atmosphere is conditionally unstable because the ELR is between the dry rate and the moist rate. If the ELR was less than 6, no matter what, the atmosphere is stable. If the ELR is greater than 10, no matter what, the atmosphere is unstable. So if it's in between, you got to do the math to find out, is the parcel actually stable or unstable at any particular altitude? All right, so here's what I want to know. What's the relative humidity, dew point temperature, lifting condensation level? What's the temperature of the air mass and the atmosphere at 6 kilometers? So what do we have? Air mass at 14 Celsius, specific humidity of 5 grams, ELR is 9. I also want to know how many grams will condense as the parcel rises to 6 kilometers. And what would be the temperature, specific humidity, and relative humidity of the parcel if after rising to 6 kilometers, let's just pretend it's going up the slope of the Sierras, hits Donner Summit, and then it's all downhill to Reno. So what's the relative humidity? We know it's got 5 grams per kilogram with a temperature of 14 Celsius. The maximum specific humidity is 10 grams, so that's pretty stinking easy. Relative humidity is 50%. Specific humidity divided by max times 100. 5 divided by 10 is 0.5 times 100 is 50%. What else do I want to know? Dew point temperature. Look that up. That was easy. 3 Celsius from the chart. So what's the lifting condensation level? Well, the dew point temperature is 3. The temperature is 14. 14 minus 3 is 11 divided by 10. It's going to give us a lifting condensation level of 1.1 kilometers. So the parcel is going to rise and cool by 10 degrees per kilometer until it hits the lifting condensation level. So at 1.1 kilometers, it will have cooled to the dew point temperature of 3 Celsius. So what's the temperature of the air mass and the atmosphere at 6 kilometers? Again, atmosphere is easy. 6 times 9, it's 54 Celsius colder. It was 14, so 14 minus 54 is negative 40. So the lifting condensation level we just figured out was 1.1 kilometers. The temperature there is 3 Celsius. So the temperature of the air mass at 1.1 kilometers is 3 Celsius. So now it's going to go from 1.1 to 6 kilometers, right? 4.9 kilometers cooling at the moist rate of 6. So we just go 4.9 times 6 is 29.4 colder than its temperature at 1.1 kilometers, which is 3 Celsius. So 3 Celsius minus 29.4 Celsius is negative 26.4 Celsius. Yeah, we just did that. So the atmosphere is negative 40. The parcel, the air mass, is negative 26, so it's unstable. So now we have an air mass at negative 26.4 Celsius. I want to know how many grams of water vapor condensed. The maximum specific humidity from the chart, you just look it up, negative 26.4. So the maximum specific humidity is 0.5 grams. We had 5 grams when we started on the ground because that was given. It now has 0.5, so it lost 4.5 grams of water vapor as it rose. So what would be the temperature, specific humidity, and relative humidity of the parcel if it sinks down to 1.5 kilometers? Okay, so the air mass at 6 kilometers has a temperature of negative 26.4 Celsius, so the maximum specific humidity is 0.5 grams. Oh, an incredibly important point I totally forgot to make. Once the parcel cools to dew point, water is condensing. If you keep lifting it and cooling it, more water will continue to condense. So once a parcel hits dew point, if it keeps rising, it'll still be at 100% relative humidity. So the air mass started with 5 grams. Now it has half a gram, so it lost 4.5 grams of water vapor. We know that. As the parcel sinks, it's going to heat up at the dry adiabatic rate of 10 degrees. As the parcel sinks, the maximum specific humidity is going to go up because the temperature is going up, but it's not gaining any moisture. The max is going up, but the specific humidity is going to stay whatever it was when it cooled. So the air mass has a specific humidity of 0.5 grams. As it sinks from 6 kilometers down to 1.5, that's going to be 4.5 kilometers of sinking. It's going to heat 10 degrees per kilometer, so it's going to get warmer by 45. So we know its temperature is negative 26.4. Negative 26.4 plus 45 is 18.6 Celsius. So now we know what the temperature is. We know what the specific humidity is because it's the same as it was on top of the whatever mountain that was at 6 kilometers. So using the table, round the temperatures to the nearest degree to get the max specific humidity value. So air mass is 18.6. We're going to round that to 19 because the maximum specific humidity chart only has whole numbers on it. So 18.6 rounds to 19. At 19, the maximum is 13.9 grams. So the air mass is 18.6 Celsius. The specific humidity is 0.5 grams. The relative humidity equals the specific humidity, 0.5, divided by the maximum. The maximum at 19, remember, was 13.9 grams. So that works out to 4%. The relative humidity is 4%. The specific humidity, yeah, you only lose water. It works like a one-way valve. You only lose water, you never gain water. If the air mass moved over the ocean, it would rehumidify. If it moves over the Great Lakes, it would pick up more moisture. But if it's just rising and sinking, for example, if it's sinking in Reno and getting warmer, Reno's a desert, so it's not going to be picking up any water vapor. So relative humidity, 4%. Oh my gosh, another example? That's like Christmas. Stop, you're too generous. So given air mass at 10 Celsius, specific humidity of 3.8 grams, environmental lapse rate of 7, and temperature on the ground is 10 Celsius. So I'm going to ask the same questions. What's the relative humidity? What's the dew point temperature? What's the lifting condensation level? Okay, so what's the temperature of the air mass in the atmosphere at 6 kilometers? Is the parcel stable? Same kind of questions. What would be the temperature, specific humidity, and relative humidity of the parcel if it sinks down to 2 kilometers? So what's the relative humidity? Well, we looked it up. The specific humidity is 3.8. The maximum is 7.6. So the relative humidity equals 50%. A specific humidity of 3.8 grams means a dew point temperature of 0. Boy, that's going to make the lifting condensation level easy. Temperature on the ground is 10. Dew point temperature is 0. 10 divided by 10 is 1. So temperature on the ground minus the dew point, 10 minus 0 is 10 Celsius of cooling. So 10 degrees of cooling divided by the rate of cooling of 10 degrees per kilometer gives us 1 kilometer of rising. So the lifting condensation level is 1 kilometer. So the temperature of the air mass in the atmosphere at 6 kilometers. The parcel rose and cooled to 1 kilometer. It cooled to dew point at 1 kilometer. Now it's 0. And then it rose from 1 kilometer to 6 kilometers, cooled at the moist rate. So we've got 5 kilometers of lifting at 6 degrees of cooling per kilometer. So it's going to be 30 degrees cooler than 0. So the temperature of our parcel is negative 30. 6 kilometers of rising and cooling. So the temperature of the atmosphere is going to be 42 Celsius cooler. Since the ELR is 7, 6 kilometers of rising. As you go up through the atmosphere is just sitting there because this is the environmental lapse rate, remember? So it's the unmoving atmosphere. So the atmosphere is going to be 42 Celsius cooler. It was 10 on the ground. 10 minus 42, negative 32 for the atmosphere. The parcel is negative 30. So the parcel is unstable at 6 kilometers because 30 Celsius is warmer. I'm sorry, negative 30 Celsius is warmer than negative 32 Celsius. So the parcel is negative 30 Celsius at 6 kilometers. As it sinks from 4 kilometers, it sinks 4 kilometers down to 2 kilometers because I've asked you what would the temperature be if it sinks down to 2 kilometers. So as the parcel sinks 4 kilometers, it gets warmer 10 degrees per kilometer. So it's going to warm up by 40 degrees. Negative 30 plus 40. So the parcel is going to be 10 degrees at 2 kilometers. The parcel cooled down to negative 30. So the specific humidity at negative 30 was 0.3 grams. So now we can figure out the relative humidity. The temperature, given these temperatures, the parcel is now 10 Celsius with 0.3 grams. So we look it up on the chart, and 0.3 at 10 degrees, you can have 7.6. So 0.3 divided by 7.6 is 0.039 times 100 is 4%. So the relative humidity is 4% now. So the total grams of water vapor lost from the very beginning. We started with 3.8. We ended up with 0.3. So we lost a total of 3.5 grams of water vapor. And that's it for Lab 7 for the intro video. Like I said, there's a whole lot of information being thrown at you all at once. If you have questions, please show up during the Zoom hours. I think watching this over again might be helpful. You can always back it up, watch it again until it begins to click. I have also put up a page of practice problems for you, very similar to these problems that you can do before you have to do the lab exercise. They're not for credit, but as you do them, hopefully the idea is it starts off with a whole lot of ideas all jumbled together, and it's very confusing. But if you go through them over time, it'll make more sense, and eventually it'll just be busy work. You look at it and go, oh yeah, I got it. I just have to go through the steps to come up with the answer. But by doing the problems again and again and again, you'll learn how to do it. It'll become easier. And that's really my best advice would be watch the video again, do the practice, the pre-quiz. The pre-quiz is concentrating on just general concepts. And then, like I said, there's a whole page of sample problems with another answer sheet so that you can work through those, figure out what you're doing right, figure out what you're doing wrong before you jump into the actual lab exercise. That's it. Good luck on Lab 7.